Welcome, friends. So, in the last lecture, we have introduced corona and we have discussed the reason of formation of corona and regarding the breakdown strength of air and depending on different weather condition, the breakdown strength of air varies. Now, in this lecture, we shall see some mathematical aspects of corona. That means at which voltage the corona process starts and what is the power loss of corona, something like that. So, we start with different terms. So, first we define first, it's called, the first term is called is critical disruptive voltage. Okay, is critical disruptive voltage. What is the definition? The minimum phase to neutral voltage at which corona begins. So mathematically it is given by this formula. So what is the definition? The minimum phase to neutral voltage at which corona begins. That means the beginning process to start with that means the minimum phase to neutral voltage required to liberate one electron from the metal surface. That is the beginning of the corona. So that voltage is called critical disruptive voltage. And mathematically it is given by Vd, which is critical disruptive voltage, is equal to M0 delta G0 R into ln d by R. So what is these terms? So delta, you know, it is called air density correction factor, discussed in the previous lecture. R is the radius of the conductor. Radius of the conductor. E is distance of two electrodes. Now we have two new terms, not two, we have one now. What is G0? G0 is the breakdown strength of air. Breakdown strength of air at STP, which is equal to 30 kV peak per centimeter. Of course, at STP. Now, what is M0? This is a new term associated or introduced. M0 is called irregularity factor or roughness factor. M0 is called irregularity factor or roughness factor. What is that? Now, due to, suppose we have a conductor like this. Suppose we have a conductor like this. Now, due to pollution or due to many reasons, the surface of the conductor is not so clean. It is polluted with maybe some dust particle and some other darts, okay, other impurities as well. So this surface of the conductor itself, it's not clean. So if it is clean, then it is a enemy environment or enemy environment for corona. However, if the with dirt or with dirty surface, it will be a friendly atmosphere for corona to happen. Friendly atmosphere for corona to happen. Why? Suppose if we see, suppose Suppose I am considering this is a part of the metal surface. Okay. This is a part of the metal surface, and due to the impurity, suppose we define or we locate 2 points. We locate 2 points. This is 1 point and this is 1 point. Okay. Suppose impurity A is located at this point and impurity B is located at this point, B point. Suppose due to the presence of these two impurities, you see this effective distance reduces drastically. Effective distance between this that means the air gap between these two impurities reduces drastically. So due to these impurities, your V by D, this ratio will be increased enormously. So due to this factor, dirty surface, that means the surface full of dirt, it is not a very healthy environment. It is a friendly atmosphere for corona to happen, because you require very less amount of voltage to have the electrical spark between these 2 points. And since these two sparks, this corona is not occurring throughout the surface of the material and it is only confined to these 2 points, sometimes it is also called local corona. It is also called local corona. So due to this, in order to account this effect, we introduce a factor. It's called irregularity factor or roughness factor. It is roughly, its value is roughly around 0.7 to 0.9, or depends from application to application. So if it is a smooth surface, then M0 is 1, no issue with that. But if it is a full of rough, which is very practical, this is roughly it's 0.7 to 0.9. So that means you require only 70 to 90% voltage than that of in contrast to the clean surface. So you are requiring 20% or 30% less voltage to break the gap. That is the difference. That is the meaning of the UC. So roughness factor, so conductor surface should be rough, not rough, conductor surface should be clean. Now the next term is called visual disruptive voltage. What is visual disruptive voltage now? You see the minimum, the definition changes, the minimum phase to neutral voltage at which corona is visible. So one is corona begins and another one is corona visible. Now you require some more amount or some time to so since the inception of the corona from that one electron, you require some time to gap this entire or to breach this entire gap with the excited electrons, and you require more amount of voltage. So when this corona is visible, okay, by eyes, visible by eyes, then that voltage is called visual disruptive voltage or visual critical voltage. So it is roughly, or it is changed by a factor of this term, 1 plus 0.3 by delta into R. Otherwise remaining parts are same. This is the enhancement factor. This factor is the enhancement factor. Now thirdly, what is the corona loss? When corona happens, a definite power loss will occur. So that is given by this formula. It is first term is 244 by D, 244 by delta, that is air density correction factor. Now you see frequency is playing an important role. More frequency means more power loss. Root under R by D, then phase voltage minus disruptive voltage. So unit should be kilowatt per kilometer per phase. So this is the formula for power loss during corona. Now next, coming to the factors affecting corona. What are the factors that influencing corona? First of all, ion density. As I told you, more number of ions per unit volume will be familiar or will be helpful for corona to occur. State of the ions, that means whether those ions are in excited state or in normal state. And number 3, mean free path. So you can understand if one object runs from this point to that point, y, and if some other object, if it runs from x to z, so it will require less energy to move for the second case. So mean free path should be important. So the less it will travel, the more energy it will gain. What are the physical conditions? The applied voltage, the more voltage you apply, more it will be helpful for corona to form. Contour and state of the surface, as I told you, the roughness of the surface is helpful for corona to happen. And the length of the air gap, if the air gap is more, the less chance of corona being happen. Okay. And nature of the conductor, if we have the stranded conductor, we have the high probability of getting corona. Why? Because we have these teeny air gaps, right, in these zones. We have teeny air gaps in these zones. You see these zones. Very teeny air gap. So as you see, V by D ratio is enormous regions, this teeny air gap. So due to that factor, the stranded conductor is not good for corona. And bundle conductor is, if we bundle conductor, the corona will reduce. Why? Because if you see, this is the this is the bundle conductor with 3 subconductors, the effective radius of the conductor is increasing. So that is why the formation of corona or the chance of having corona is less. Next important term is local corona. I have already explained what is local corona. Due to irregularities on the conductor surface, due to the rough or dirt, corona sometimes confined to a particular zone. It is called local corona. Okay, I have already shown. Suppose this is a part of the conductor surface. We have a one dirt here, one pollute here. So this gap distance is very less. So for this zone, E by D ratio or V by D ratio is very large. So corona start forming, or corona starts in this particular zone, but not for the entire conductor. So it is this zone actually corona is happening. It is for this zone only corona is happening, but not for the rest of the conductor. That is why it is called local corona. Is called local corona. Now next we shall shortly see what is the advantages of corona. Now if corona comes, so it acts as a safety valve or safety shield against the step waveform caused by lightning or switching. So if a lightning comes or switching comes, this type of waveform comes which have a very steep wavefront, very high, that means the rate of, that means DVDT is extremely high. The rate of change of voltage is extremely high. So if corona comes, this type of voltage is bypassed using that corona. What are the disadvantages? Number 1, definite power loss. We have some definite amount of power loss will be there. Number 2, ozone gas will form, which is not good. Ozone gas will form, which is not good. Why? Because it will react with metal surface and it will corrode the metal surface. So the metal body will be destroyed soon. Okay. Now with this, we shall shortly see some problems. So we have some problem. We have problem 1. We have a 3-phase 220 kV 50 Hz transmission line, equilateral spacing of side 2 meter. So we have side 2 meter. So D is equal to 2. So we have D is equal to 2 meter. The conductor diameter is 3 centimeter. So we have conductor diameter is 3 centimeter. That means radius is 3 by 2. That means 1.5 centimeter. What else is given? Air density factor and irregularity factor is roughly or respectively 0.95 and 0.83. So air density factor delta is 0.95 and irregularity factor, that is M0, which is equal to 0.83. So you need to evaluate disruptive critical voltage, that is you need to evaluate VD first, then you need to evaluate loss, corona loss. So these two you have to evaluate. So we quickly write down what is the VD. So formula, if you go by formula, it is M0 multiplied by delta times G0, that is the air density correction factor with the breakdown strength of air at STP. Then we have R, then ln D by R. So this was the formula. So if we put 1 by 1, 0.83 into 0.95 into 30 kV peak per centimeter into R. What is R? 1.5 centimeter. With that, we need to multiply this term ln D by R. So what is D? D is 2 meter. And what is R? It is 1.5 centimeter. So you need to multiply this with. So if you evaluate this, it will be coming as 173.6 kV peak. Or you can convert them into RMS value as well, 173.6 by root 2 kV RMS. So this is the disruptive critical voltage. Now what is loss? Let us evaluate that part also. So what is loss? Power loss during or due to corona. First we have 244. What is the formula? First let me write down the formula. 244 by delta. Then we have F plus 25. Then root under R by D. Then V phase minus VD whole square into 10 to the power minus 5. Unit should be kilowatt per kilometer per phase. So 1 by 1 if we put, it should be 244 by delta. Delta is 0.95. F plus 25, that means 50 plus 25 multiplied with root under R by D. So R is 1.5, that should be taken into meter, and D is 2 meter. With that, V phase. Now what is V phase? V phase is 220 kV. V phase is 220 kV. So 3 phase. So you need to divide this as 220 kV by root 3 minus this value 173.6 0.6 by root 3, that multiplied with 10 to the power minus 5. Now if you solve this, you will see it will be coming as 0.3106 kilowatt per kilometer per phase. So therefore we have total power loss. So therefore we have total power loss. So it should be multiplied by 3 because it is a per phase. So total loss will be 3 multiplied by 0.3106, which is equal to 0.9318 kilowatt per kilometer. So this is how you solve this problem. We have another problem. A 3-phase equilaterally spaced transmission line has a total corona loss of 55 kilowatt at 110 kV and 110 kilowatt at 120 kV. So what information we are having? So we have power loss, corona power loss is equal to 55 kilowatt at 110 kV. Also, and second condition, the corona loss is 110 kilowatt at 120 kV. So now you need to evaluate what will be the corona loss at 125 kV. So let me see how this problem can be solved. So you know what is the power loss. P loss is equal to 244 by delta F plus 25 root under R by D, then V phase minus VD whole square into 10 to the power 5, which should be kilowatt per kilometer per phase. Now as you can see, this 244 by delta is constant, F plus 25 is constant, root under R by D is constant. So you can directly write P loss is directly proportional to V phase minus VD whole square. Or you can write P loss is equal to some constant K times V phase minus disruptive voltage whole square. So we have, if we use this first condition, so we have 55 kilowatt, that will be equal to K into V phase minus V. So we have 110. So we have 55 kilowatt at 110 kV. So we should put the value 110 by root 3 minus VD whole square. This is equation 1. And similarly we can write 110 kV or 110 kilowatt at 120 kV, right? So we can write 110 is equal to K into 120 by root 3 minus VD. This is equation 2. So now if you do like this, equation 2 by equation 1. So what we will get? 110 by 55, that should be equal to 120 by root 3 minus VD square whole square, 110 by root 3 minus VD whole square. So if you solve this, you will get VD is equal to 49.57 kV. So from equation 1, from equation 1 you can put 55 is equal to k into 63.5 minus 49.57 whole square. So if you solve, our k will be is equal to 0.2834. This 63.5, where from it is coming? It is actually 110 by root 3. So finally, we will now write, we will solve final part, which is what will be the corona power loss at 125 kV. So power loss at 125 kV is equal to, you know, k is 0.2834. So we have 125 by root 3 minus 49.57 whole square. So if you solve this, you will get 145.75 kilowatt. So this is the solution for you. So we have seen different aspects of corona. So at that means the voltage at which corona begins, it's called visual, sorry, not visual, it is disruptive voltage, and the voltage at which corona is visually seen, it is called visually disruptive, visual critical voltage. And we have seen some definite power loss will be there during the corona. Also, we have seen the advantage and disadvantages of corona and different influencing factor of corona. And thereafter, we have seen 2 numerical problems on corona. So this is the end of corona because it is a very small chapter. I hope you will find this topic or this chapter is very easy and interesting to you. So with this, I am ending this chapter here. So from the next lecture, we shall start a new topic or new module. Thank you.